Metals are incredibly significant that we've named entire periods of human history after them. One of them is the Iron Age, with its association with the metal iron. Some of the earliest evidence of iron being used as a material goes as far back as 3500 BC in ancient Egypt, where iron was taken from Media. One of the Egyptian pharaoh was buried with a dagger made of this material, but meteoric iron was the only natural occurring source of iron at that time, because iron readily reacts with oxygen to form the iron ore. There is no oxygen in space, so meteors deliver this material to Earth in the form of humans could use without having the technology to extract it from its ore. The Iron Age began at various points across human history as we started to learn how to extract iron from its ore. Iron is found on group 8, period 4 of the periodic table in the D block. Its atomic number or proton number is 26. It is solid at room temperature with an electronic configuration of argon plus 4s2 and 3d6. Its melting point and boiling point are very high, and it is fairly dense. Its relative atomic mass is 55.845, and its key isotope is iron 56. Iron, being a type of metal, exhibits metallic bonding. In metallic bond, the valence electrons from the s and p orbitals of the metals are delocalized. Instead, they form a sea of electrons around the positively charged metal cations, where they are shared. Usually metallic bonding is quite strong, so they have very regular structure and have high melting and boiling point. They also have very high density because of this. The basic most common type of iron ores are magnetite and hematite, which has to undergo redox reaction to obtain iron in a blast furnace, where coke, iron oxide or iron ore, and limestone is added to a blast furnace where hot air is blasted into it. The carbon reacts with oxygen to form carbon dioxide. Carbonate or limestone decomposes into calcium monoxide and carbon dioxide. Carbon reacts with carbon dioxide to form carbon monoxide. Ferric oxide then reacts with carbon monoxide in a redox reaction to obtain iron and carbon dioxide. And the calcium monoxide reacts with the sand to form the slag. However, iron smelted from the blast furnace has a very high carbon content and is therefore incredibly brittle. It needs to be converted to other forms of irons through decarburizing. This is where alloys come to play. Alloying is to mix metals with metals or non-metals or both. There are two types of alloys, substitutional and interstitial. Substitutional alloys are when we mix elements of atoms that are about the same size. Interstitial alloys where atoms' sizes vary greatly, so the smaller atoms fit into the spaces between larger atoms. This is what happens to carbon in the iron. The type of alloys affect the grain structure of the metals. The type of iron alloys are pig iron, which is what we get from a blast furnace, and it is not very useful. It has a high carbon content of about 3 to 4%. Steel is the most useful type, with around 0.07 to 1.3% carbon. There are a few types of steel. Stainless steel is one of them. It is least prone to rust due to the nickel and chromium element added to it. This is a type of substitutional alloying. There's also mild steel and wrought iron, which is very ductile and malleable with around 0.05 to 0.25% carbon. The properties of pure irons are: it is soft, it has a very low specific heat capacity and therefore is a very good conductor of heat. It is a good conductor of electricity as well due to the free moving electrons. It is lustrous because the free moving electrons reflect the light that hits it. It is malleable and ductile if it is pure iron, and it has a very high melting and boiling point due to the very strong metallic bond. Metals are made of grains. The smaller the grains, the more the dislocations and the less they bend. The bigger the grains, the less the dislocation and the more they can bend. Mechanical work on the grains, like hammering it, can make the grains smaller. So at one point, there are too many dislocations in the metal to bend any further without breaking it. This is called work hardening it. There are also heat treatment, such as annealing, where it is heated until red hot, then cooled slowly. This gives it time to form larger grains and therefore restore the ductility and malleability of the metal. Quenching it is when you heat it to red hot and then cool it quickly in water, forming smaller grains which are harder and more brittle. Tempering it is after the quenched metals are quenched, they are warmed to a lower temperature and then cooled slowly, reducing the brittleness while still remaining and maintaining the hardness. The uses of irons are very prevalent in human society, in our industry, our weaponry, and our buildings. They are used to build the very tall to the very small. They are used to build the Eiffel Tower and to build bridges that link islands together. They are used in industrial manufacturing of tools and equipment, surgical tools and cooking tools, and also dining utensils. And most importantly, iron is found in human biology and many of the animals' biology, except crabs, because crabs use copper instead. But basically, iron is the part of our hemoglobin that allows it to bind with oxygen, that gives it that red color. And without iron, we wouldn't be alive. And to recycle irons is fairly simple. One of the ways would be to heat it back up and melt it and then turn it to other useful forms.